Now, this is an example of an entanglement-assisted quantum convolutional code. This one is a nice structure in that the operations that we perform on the encoding end are finite depth. Now that's sort of an analogy to the finite impulse response classical circuits. And what it means in the quantum case is if an error occurs over here, it only propagates finitely. If an error occurs on this control qubit, it can only propagate to this target qubit. It would be a problem in a sense if you were decoding and used infinite depth operations. An infinite depth operation would have the source qubit over here and the target down there. And so errors could potentially propagate through this circuit. But we're going to show an example of that later on. So anyway, this circuit right here is finite depth. It's an encoding circuit, and the circuit to decode is the exact inverse. You perform these operations in reverse order. Okay, and so those have a very nice structure. And these would be useful for a fault-tolerant quantum computing application. Okay. Now, let's talk about infinite depth operations. These are operations that we introduced because we wanted to be able to import the full classical theory into quantum convolutional coding theory. And we decided that we needed to incorporate these. Okay, and so these are operations you would perform when you're encoding, since we have an assumption that we can do noiseless encoding for some of these codes. Okay, so an infinite depth operation operates as follows. You would have C-naughts from a qubit in the first frame to the same qubit in the next frame, and so on and so forth. And it's infinite depth because you can trace a path all the way through the circuit. And in terms of the polynomial formalism, you can represent these convolutional codes with Pauli sequences, infinite Pauli sequences. And the resulting operation, if you're looking at a binary polynomial, you would use this side to represent the z terms and this side to represent the x terms. So an infinite depth operation on the x side would implement this rational polynomial, 1 over 1 plus d, which if you expand it out would be an infinite sequence of polynomials, 1 plus d squared, et cetera, et cetera. And on the z side, it would only go finitely backwards. So x errors go forward and z errors go, or z entries go backwards. Okay, and isn't it more complicated example of an infinite depth operation? This circuit right here would implement this polynomial on the x side, which would correspond to an infinite sequence, and this polynomial on the z side. Okay, so we have codes that use these infinite depth operations. Okay, and this is an encoding circuit right here. You have these finite depth operations. You perform, Alice performs then this infinite depth operation, and finally performs more finite depth operations. They're encoded. She sends her half of the qubits over a noisy channel. And then at this point, Bob would take all the qubits, perform stabilizer measurements, get classical data from that, classical syndromes, run a decoding algorithm, such as the Viterbi algorithm, correct the errors, and then perform this decoding circuit. Okay, now, it's important that the decoding circuit have finite depth operations only. Because if you had infinite depth operations, the errors that occurred over the channel, that's supposed to be here, would propagate infinitely. So if there are errors that you can't correct for over here, they would propagate infinitely through the stream, and thus we call it a catastrophic error. Okay, and when we include infinite depth operations on Alice's side, it turns out we needed to incorporate decoding operations with Bob's qubits also, so we could properly decode the qubit stream. And we have several classes of entanglement-assisted quantum convolutional codes, and we divided them up based on how we could encode them and decode them. Okay, so the first class are the ones that are the most practical, most useful for quantum computation even, because we don't have to make any assumptions about encoding and decoding. All these operations are finite depth. The second class the example I just showed you falls into the second class, and that class uses both finite depth and infinite depth operations on the encoding circuit, and finite depth decoding operations. Okay, so these would be more practical for a quantum communication scenario. And finally, this is the last class, and we included infinite depth operations in the decoding circuit, and I realized I said that I couldn't do that before, but the assumption we made is these infinite depth operations only happen on Bob's half of the E bits. And in the entanglement-assisted communication paradigm, you assume that those are noiseless. So we said, okay, we'll go ahead and do these, even though we really would prefer not to. And there are several advantages which are similar to what Todd and Igor and Minciu found for entanglement-assisted block codes, in that we could import two arbitrary classical codes. Okay, this is a very simple picture of what's going on. It's a CSS-like construction. This is a parity check matrix for a classical convolutional code. In general, it's a matrix of polynomial entries. And this is another classical binary convolutional code. You take them with the CSS recipe, and this is really just showing you Alice's side. There's a lot of steps we have to go through to get to determine the encoding circuit and the decoding circuit. But in general, you're going to have entries for Bob's half of the E bits, and I haven't shown these here. But if you read the preprint, you'll see all that there. And the result is that the rates and error correcting properties of the classical codes that you import will translate to the quantum case. Okay, so high performance classical codes will yield high performance quantum codes. And in general, if your classical code H1 encodes K1 information bits into N physical bits, and the second code encodes K2 information bits into N physical bits per frame, then this will yield an entanglement-assisted quantum convolutional code with these parameters. And this parameter C is the number of E bits that the code requires per frame. And there's a specific formula we give that depends on H1 and H2 in the paper. It has to do with the rank of H1 times H2. It's a little more complicated than that. But okay, and lastly, 1 minute. Okay. Very quickly, an entanglement distillation protocol. You can take a stabilizer code. This is a textbook problem in Mike and Ike, chapter 12. You take a stabilizer code, you perform the measurements corresponding to it, and you can produce an entanglement distillation protocol. Okay, that's well known. And in this other paper with Hari and Todd, we gave entanglement distillation protocols a convolutional structure. Okay, and we found the same result. This is the operation of entanglement distillation protocol. We found the same result. You could import classical convolutional codes for use in entanglement distillation. And in that construction, for decoding, you essentially get logical, you get sort of information E-bits from physical E-bits. In that construction, our decoding circuits were only finite depth, so that was nice. And so in conclusion, these entanglement-assisted codes are nice because they're nice to physicists because they exploit entanglement in their procedure. And importing classical codes should produce high-performance quantum codes. The last thing we'd like to connect this to, because of the connections between quantum privacy and distillation, is figuring out how to use these codes in quantum key distribution. It may be more practical use of these procedures. And of course, there's much to explore. Thank you very much.
Questions? Maybe one question. Yeah.
So maybe I misunderstood something, but when you had the infinite depth coding circuit,
Right.
it looked like all of those, the infinite depth part, all those gates communicated. Is that not correct?
Oh, the one that I was showing in the example, they don't. Because if you have a path where a source qubit is the gate operating before it is connected to a target qubit, then it has the infinite depth structure. In that example, it may not have been clear, the circles and the dots may have been small, but there was that structure there. For those gates, it was, right, so it's sort of a shorthand that, it's all C knots, it's a shorthand that Grassel and Rutler employed. You really should expand it to make it more clear, but to, so.
Okay, so I